So redox. So our glaze that we're going to use for the raku pottery it's a redox reaction. This, it's kind of hard to see. We don't have the best picture here. But this is the bowl before we fired. They glazed it and they fired it. So after we fire it once, they're firing them today. That's why they came to get the other pots. So we're going to fire them. They're going to come out looking somewhat pretty. I mean, these aren't terrible. This is rutile. It's got some lead and other made tin in it, maybe. And then you got your copper carbonate, iron, red iron, and then you've got your copper carbonate. After we fire them with the raku method, basically what we do is we'll bring both kilns in, we'll sit them in here, and then all this stuff happens out here in the courtyard. So after you fire it the third time in the kilns in here, and we burn them and stuff like that, look at the beautiful colors that come out. So all of a sudden you have like tin oxide in your glaze. When it undergoes reduction, the tin itself comes out. You have copper 2 carbonate. When it's reduced, you'll see the copper in here. This is the beautiful copper. This red streak is your iron. So there's a lot of really cool colors that come out. But again, we can't guarantee it's going to happen because it all depends where the fire hits. And we'll talk more about that later on. These are also, this is Panama red. This is what it looks like after the first firing. This is what it looks like after the raku firing. So they just change colors differently. I wish I could show you, like, I try to find pictures of where fire hit and fire didn't hit, but it's really hard to find that. Okay, rust basically happens due to oxidation reduction reactions. Basically, the iron undergoes some form of oxidation. It basically loses electrons and it combines with oxygen and it makes rust. So rust happens due to oxidation reduction reactions. There are a lot of oxidation reduction reactions around you that occur all the time. But a lot of times we see them as single replacement reactions or combinations. Fires are also oxidation reduction reactions. Fires need oxygen. They need the oxygen and the electrons on the oxygen. They want to be, they want reduction. They want to gain electrons. And we'll be talking, there's a creepy little video I'm going to show you here in a minute that kind of shows that. But I hate when you watch these movies, like I was watching Deadpool a couple of nights ago. You know, if you've ever seen Deadpool when he's in the case and they're depriving him of oxygen, but oxygen's coming in at a low rate. He's got the match and he strikes it, he puts it down by the vent, and the whole system blows up. That would not happen. Oxygen is not flammable. What would have happened is the little match he had would have burned up like that, he'd have burnt his hand, and it would have gone out. You know, sometimes knowing chemistry ruins lots of movies because you're like, that can't happen. Things don't freeze that way, or things don't look that way. It drives me crazy. I mean, now why didn't they just put hydrogen in there and it all would have worked out just fine? But no, they put oxygen. This is coal burning. This requires some oxygen. But anyway, oxidized means it loses electrons. So if I say something is being oxidized, it means it's losing electrons. If something is reduced, it's gaining electrons. I forgot what was next. And the way you remember that is by oil rig. I write this whenever I do any type of redox material. I write oil rig immediately on top of my periodic table, or my paper. Oxidation is loss, reduction is gain. That way you'll know what you're doing. Oxidation, you lose electrons. Reduction, you gain electrons. Write down oil rig. It will help you a lot. We good? Oh, it's only 9 more days. I mean to do this all day. Yay. Forgetting to put that on there.
Now, are you counting today or are you counting the
Today.
Today.
Yeah. We have, yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, because I have to be here on that day. Yes. Okay. Now here's that creepy video I was telling you about. It's weird. It's just so weird, but it makes very good points. So if you're a little confused about what I'm talking about, watch this video and it will make things very clear if you can get past the creepiness of it. And there's no words, so you have to actually read things. That's creepy. You get up electron. Hey! Hey! Up! So what would be the spectator ion in that one? Sulfate, the sulfate. This is sulfate didn't have any change at all to it, did it? It just continued on to the other side. Such a weird little video, but just It makes its points really well, though. So basically, the loss of electrons is oxidation. The ones that gain them is reduction. Metals tend to be oxidized. Remember, we have sodium is +1, magnesium is +2. All of the metals have positive charges to them. That means they all will be losing electrons. They all like to undergo oxidation. Okay, they want to lose electrons. Nonmetals tend to be reduced. They take electrons. They love taking electrons. Okay, oxidation numbers, those are also the charge, we call them charges as well. Charges and oxidation numbers are the same thing. So if you got your periodic table out, you'll know that you have your charges on there, your oxidation numbers are on there. There are a positive or negative number assigned to each element to indicate how many electrons we lost or gained. Its degree of oxidation and reduction. So you've been using oxidation numbers, we just call them charges. But the thing is this, guys, I've lied to you. I'm sorry. I know, shattered. I've told you that those are the charges here on your periodic table. That this is what happens. It's not. I left off quite a number of things because I didn't want to confuse you. Here are some of the oxidation numbers you don't know. Like, lithium's +1, we know that. Beryllium's +2. Boron can take a -1, a +1, a +2, or a +3. Nitrogen isn't -3. It could be -3, -2, -1, or a 1 through +5. I just don't put all those on there because I don't want you, when we're first learning how to do this stuff, to be confused by everything. But these are all, look at silicon. It can do +4, -4, and everything in between. The bold ones are the ones that typically they become. Okay? So there are a lot more charges out there than you're aware of. One thing you got to remember is this, though. The elements on this side of the periodic table, will typically be the ones that we're used to having charges for. All these typically are +1. All these typically are +2. And most time these guys are +3. These have a wider change of charges, and your nonmetals have a much different variety of charges. Okay? The oxidation of any element is always 0. So if it's elemental, the charge is always 0. So if you have Fe, we write a 0 charge above it. If you have Cl2, there's a 0 charge above it. Okay? Elements are zeros. No charge at all. Okay? Yes? Now, if they're binary ionic compounds, we're back to our ionic compounds again. Binary means how many elements? 2. So if I have calcium chloride, the charges go just as you would normally do them when you're writing formulas. What's the charge going to be on calcium? +2. How do you know that? Just go backwards. That 2 comes up there. That 1 goes over there, right? So it's +2 and a -1. Binary ionic compounds are easy. Just go backwards with the subscripts. But I've got 2 calciums, -2 chlorines gives me a charge of 0, right? Now, if they're molecular compounds, you have to kind of look at a few different things. You have to look at the electronegativities. Remember your electronegativities on the back of your periodic table? You have to see which one's more electronegative. That's going to tell you which charge to start with. So, if I look at H2O, What's more electronegative, hydrogen or oxygen? Oxygen is. So oxygen has a charge of what? -2. Oxygen's always -2 unless it reacts with fluorine. Then it takes on some weird numbers. Okay, Kevin? So this is +1. So I got +2 here, -2, it equals 0. Does that make sense? A little bit. Yes? These are some examples. Now notice beneath here. Okay? I don't like the way they wrote them. I found this and I thought, oh, it's kind of nice to show you how to do this, but wow. So carbon dioxide. Here's how you would do this. CO2. Since there's no external charge on this, it's going to have to equal 0. I know oxygen's always a -2. These up here, these are my oxidation numbers. Down here, it's like my tally. It's like when I balance equations, how you write everything beneath the equation. So 2 times -2 is what? -4. Remember, this has to equal 0. So this is -4. What's carbon have to be? A +4. Because 4 times that 1 gives me a +4. So I say, what's the oxidation number of carbon? It's +4. Don't look at these numbers down here. Does that make sense? Those are easy. When you do binaries, they're simple. But what if I have something like this? So the most electronegative of these elements, probably oxygen, yep, is oxygen. So we're going to start with oxygen. Oxygen has a charge of what? -2. So -2 times 4 is what? -8. This has to equal 0. Hydrogen always has a charge of what, especially when it's first? +1. 1 times 2 is 2. What do I add here to make that equal 0? This sulfur then is going to be a +6. +8 minus 8 equals 0. If I say, what's the oxidation number of sulfur? You would tell me 6. +6. Do not, this is just tally marks. I don't have to worry about that at all. But I would do those. If you don't do that, you're going to be very confused. The last group, I kept telling them, do it the way I'm showing you up here. They question after question, and then they didn't get a chance to do their homework. Okay? Because this isn't what we're going to do today. Now, what if I have this? Kevin, I need your eyes open, okay? So if I have SO4 minus 2, sulfate ion. Okay? Oxygen has a charge of what? -2. So 2 times 4 is -8. But now this whole thing has to equal a -2 because the overall charge is not 0. There's a -2 charge in the whole thing. Okay? So if this is -8 and that has to be -2, what does sulfur have to be? +6. So sulfur is a +6. Does that make sense? It's relatively easy if you just don't fight it. But if you like, then it's going to be painful. We good? Okay. Let's practice some of these. Oh, you'll just see a little negative mark. That means -1. Most people, when we write these, don't put -1. You put a negative. There you go. Make sure it's all right. Okay. That was an awfully thick stack. So you're going to introduce your personal shadowing you, Cole?
This is Javon. He goes Northwest and he's coming to the next
Nice. Welcome to Ross. Are you in chemistry this year? No? Good. So we get you to next year. Yay. You're welcome. So then give these a try. Let me know if you need help.